Hello, everybody. Welcome to Blue Marble Science. Brian's logic says airplanes can't possibly work on a globe. Well, it's not like we haven't explained this about 1,000 times, but Brian has got some brand new ideas that just won't work. Warning, severe facial and monitor damage alert is in effect. Get out those oven mitts, push the monitors back out of punching range, and let's light this dumpster fire and have some fun.
Aircraft fly with their noses between 1 and 4 degrees above horizontal on average. The reason they fly this way is due to how aircraft are designed to fly, by using air pressure differential above and below the wings. Aircraft are pushed ahead through the atmosphere by thrust.
Atmos? You're going to start out with the Atmos, and then you're going to get mad if we don't take you seriously? Come on, Brian.
And the wings of the aircraft are designed in such a way to create and take advantage of a pressure differential, where faster moving air glides over the top of the wing, causing a lower pressure system, and slower moving air glides underneath the wing, causing a higher pressure system. Due to entropy, this causes lift.
No. No, Brian. Just no. Air flowing over and under a wing is not entropy. Where do you come up with these ideas?
As the higher pressure under the wings strive for equilibrium with the lower pressure above the wings. So, the more thrust that is imparted by the pilot of the aircraft, the faster the air flows over the top of the wings, and the faster the air, the lower the pressure. And as we all know, an increase in pressure differential will mean an increase in entropy.
You're an idiot!
So, more thrust, the greater the entropy. The greater the entropy, the more lift. The more lift, the more tilt the nose of the aircraft will have upwards.
Right off the bat, you've got this all fouled up, Brian. It's not the thrust of the engine that causes the nose to tilt up. That's what the elevator of the airplane does. Let's at least get our terminology straight. We have a wing, and the wing has ailerons, and the ailerons control the roll axis of the plane. At the back, we've got a rudder. The rudder is used to control the yaw axis of the plane. And then we have an elevator. The elevator is what controls the pitch of the airplane, or the position of the nose of the plane. The elevator has a trim tab that's used to remove the pressure that the pilot would have to hold on the control yoke. If that trim tab is set for the airplane to be flying in a nose-down attitude, increasing the thrust will simply get you to the scene of the crash a little faster.
So, just before I move on there, okay, here is an aircraft wing. Um, Fast moving air over the top, slow moving air underneath. Okay, so you have high pressure underneath and low pressure at top. So high will go to low, causing lift of the airplane. So here is from NASA. So thrust is pushing, pulling, pushing whichever the plane forward. You have drag, which is the air resistance, causing a pull back the way because it has to flow through air. You have weight of the airplane, which will cause it to want to go down. Then you have lift caused by thrust, which will allow it to stay up. Okay.
Lift is not caused by entropy or thrust, Brian. Have a look at these airplanes. They don't have any thrust, but those wings produce an enormous amount of lift. Lift results from higher air pressure below the wing and lower air pressure above the wing. Now, there's a key factor to keep in mind, and it is the direct relationship between the density of the air, we call that rho, and lift. If rho changes, lift changes proportionally. In other words, the more dense the air is, the more lift you produce. We'll get back to that in a minute.
So more lift than weight, the plane will rise. More weight than lift, the plane will fall. The more drag than thrust, the plane will slow. More thrust than drag, the plane will accelerate. Okay, so the more thrust, right, will cause more lift. So the more thrust, the more lift, the more lift, the more the nose of the airplane will tilt upwards. Okay?
No, it's not okay. It is not the thrust that controls the pitch of the airplane. The pitch of the plane is determined by the forces applied to the tail of the plane. If airflow across the tail, across the elevator, is pushing down on the tail, that will lift the nose of the plane. The plane will rotate about the center of gravity in the pitch axis. Conversely, if the force on the tail is pushing up, that will cause the nose of the plane to go down. This has nothing to do with thrust. You've got this totally wrong.
So, and the more thrust, the more lift that is created, then the more the weight of the plane is overcome, and the more thrust creates the lift and also counteracts the drag, and the lift also counteracts the drag. So that's the basics of this effect. Okay, but a byproduct is the nose tilts up the way. So the more thrust, the more the nose will tilt up the way.
And somewhere in there, you said the lift counteracts the drag. Oh boy.
This is Houston. Say again, please.
Houston, we have a problem.
Okay, because it causes more lift, and the lift causes the pressure differential, which causes the plane to tilt up the way. So the plane's nose is tilted up the way. So here we have the purple line. If it's extended, let's just say globe out. Okay, I have written in down here. Here you have the plane going forward, right? So the plane is trying to go in a straight line like this yellow line here, right? But on this model here, the globe out model, it has to be doing this, right? Going down this way. But it's trying to go forward, right? Because that's how it flies. But actually what happens is as it flies, the nose comes up the way. If you can see this yellow arrow here. So what's actually happening is it's flying forward, but with its nose tilted up the way. So it's flying forward at a slight angle, okay? But it's still flying in a straight line, horizontal line forward. But it's flying with its nose above horizontal, because this would be horizontal, but this would be where its nose is, tilted above horizontal. So engine power increases lift, and lift causes the airplane's nose to tilt upwards from horizontal. Here, these lines here, making flight over a consistently curved surface a physics impossibility.
What you just said is one of the most insanely idiotic things I have ever heard.
At this point, Brian has himself hopelessly confused. When Brian talks about the nose of the plane tilting up, what he's trying to talk about is the angle of attack of the wing. The angle of attack of the wing is the angle that's formed between the chord line of an airfoil and the relative wind. Don't be confused by the term wind. That is simply the apparent movement of air opposite the direction of travel of the airplane. But there's something I want you to take a look at the bottom. As we go from level high-speed flight to level cruise speed flight to level low-speed flight, that angle of attack has to change. And that results in something that every pilot knows. Pitch controls airspeed, and power controls altitude. I can change the altitude of the airplane by doing nothing other than changing the power setting. If I increase the power without making any change to the pitch, the aircraft will climb. If I decrease the power without making any change to the pitch, the airplane will descend. In steady state flight, lift has to equal weight and thrust has to equal drag. If that's not true, the aircraft is either climbing or descending or speeding up or slowing down. You see the lift equation on the left there, and it simply says that lift is the coefficient of lift times the density of the air the plane is flying in times the square of the airspeed times the surface area of the wing divided by 2. We only need to talk about 2 of those factors. The lift coefficient C sub L, depends on the angle of attack. We have charts that tell us, for a given angle of attack of the wing, what the lift coefficient would be. The other factor is the density of the air. We call that rho, and that's dependent on the altitude the plane is flying at. Our atmosphere has a pressure and density gradient, and we all know that. Atmospheric pressure and the density of the atmosphere decrease as we go up in altitude. That means, for a fixed angle of attack, a wing at lower altitude will produce more lift than the same wing at the same angle of attack at a higher altitude. By the way, that area of high pressure under the wing and low pressure over the wing are areas of gas pressure without a container. Here's what happens in reality. We have our Cessna, and we have that Cessna trimmed to fly at a particular altitude. If for some reason the aircraft were to try to climb, it would be climbing into an area of less dense air, and that will cause it to lose lift. Now weight is greater than lift, and the plane will automatically descend to the altitude it was trimmed for. On the other hand, if the plane tries to descend, the opposite happens. It descends into an area of more dense air. That means the wing will produce more lift, and now lift exceeds the weight of the plane. The plane will try to climb, and it will return to the altitude it was trimmed for. It's just this simple.
So just going to go back down now. So from this, we can conclude that when an aircraft is flying at around 550 miles per hour, which is around the average speed for commercial Boeing 777, etc., that the nose of the aircraft will invariably be above horizontal by a couple of degrees, as it has no choice under those conditions. You see, aircraft can't not fly with their noses a few degrees above horizontal, as that is how they are designed to fly at cruising altitude for extended periods of time and distance. And every pilot must learn this, as it's a crucial part of information to know for every pilot.
And every pilot does know that, Brian. Every pilot knows that the airplane is flying at a constant altitude if it's in level flight. And in level flight, the pressure of the atmosphere and the density of the atmosphere is relatively constant. The aircraft is always referenced to the gravity vector. That keeps the angle of attack the same no matter where you are over the top of that really big spherical Earth thingy. And the aircraft simply follows that line of constant pressure right around the curve. It couldn't work any other way, Brian.
I see. So your argument is that in respect to aerodynamics and achieving lift, it wouldn't be achievable for a sustainable flight if you were descending over a sphere edge. You wouldn't be achieving lift because you'd be nosing down.
Well, the thing about it is that you have to, when you add thrust, you create more lift. And when you create more lift, you create more tilt of the nose. So the plane is always, once it does lift, the nose of the plane is always tilted above horizontal, always. It just depends on
So after forgetting that airplanes have tails and control surfaces, and ignoring the fact that there is a density gradient in our atmosphere, Brian is now over at Nathan Oakley's channel seeking technical advice. Somehow, I don't think this is going to end well. Hey, thanks for watching. Hope you guys enjoyed it. Don't forget to hit those buttons down there. Shout out to the patrons and PayPals. I really appreciate everything you guys do. And I guess we'll see you on the next one. Hey, Gladys. We're out of here.